as I told you, this section is not included for the exam, all these sections. So we'll go into another type of healing moment now. We were talking about different types of healing. First we talked about healing due to grain. Of course there is a lot of healing. First we talked about healing due to the shift of a horizontal shift of a weight. We came into healing due to grain, then healing due to wind. We have done so much. Now there is one more thing left, that is healing due to turning. Now what this suggests is that we have a ship initially that is moving in a straight line. Now if the ship is made to turn like this, okay, it is asked to turn like this, what will happen to the ship, means in terms of healing. Of course the ship will turn. Now we have to see if there will be any effect of the turning on the healing. So all that is happening is ship is moving straight, then let us suppose that the ship has to go there, that means ship has to turn, so it has to go in an arc. So once that happens, will the ship heal? That is a question, okay, in which direction, that also we will see. Okay, now let us assume that the ship is healing, or the ship is turning through a radius. This radius is r, Tc stands for turning circle, radius of the turning circle. So this is the turning circle, so the ship is turning like this up to this. Now this is r Tc. Now as you can imagine, when the ship turns, or when the ship starts going in a radius, obviously on it a centrifugal force will start to act. That centrifugal force is given by F, we will call it Tc. It is a centrifugal force caused due to the turning, is given by, first of all, the acceleration. Acceleration is v square by r. Let us assume that the ship is turning with a velocity v, therefore v square by r Tc will give you the acceleration, into delta of the ship will give you the force due to the centrifugal force, which is the force that is acting away from. So if the ship is turning like this, at the center, we assume that the centrifugal force acts at the center of gravity of the ship, okay. So at the center of gravity of the ship, there is a force that acts towards, away from the circle. So if the circle is like this, the ship is turning like this, let us say, this is the center of the circle. So away from the center, like this, a force acts, okay, centrifugal force, like this it acts. So v square by r Tc act, into this is the force acting. Now similarly, you can imagine this force will try to push the ship away, means it will try to displace the ship, but water resists it, means water does not allow the ship to move, means of course ship moves like this, but like this. This force, the centrifugal force, is trying to push it like this, but water prevents it, okay, water stops it from moving in that direction. So there is a reaction force from the water. That force most likely becomes equal to the centrifugal force, such that the forces balance. So the ship does not move like this, okay, laterally it does not move, or transverse direction it does not move. Actually there are names for each of these motions, means this is called heave. When a ship moves like this, you call it heaving. This is called surge. I believe this is sway, okay, this is called sway. So the ship tries to sway, but it prevents it from swaying. The water prevents it from swaying, and as a result that force is the same as this force, because force is balanced such that the ship is not moving. Ship is not moving in this direction, ship is moving longitudinally, of course in the straight direction it's or in the radius it's moving, but it's not pushed like this. This movement is prevented, and this force from the water will act at a distance of, means where will the force, it will be uniformly distributed from the bottom of the ship to the point where the water ends, or the water starts rather. So between the air water interface, from that point to the bottom of the ship, that is the distance over which the water force will be acting. So this water force can be assumed to act at that centroid, that is at the middle of the draft, it is at T/2, okay, all right. Therefore there is a force, there are two forces now, one force acting at kg, that is at the center of gravity, which is the centrifugal force, it is like this, and there is a force acting from the water at T/2 like this. Therefore there is a force like this and a force like this, separated by a distance of kg minus T/2, okay. Kg is this distance, this is T/2, kg minus T/2 is the distance between these two forces. So this force is actually causing it to turn, tilt like this. So it might be slightly against your intuition. The ship, when it tries to turn like this, it will actually tilt like this. it won't tilt like this. Means when a bicycle and all we have think it will tilt like this, it's not like that. For a ship, for the other thing it's slightly different, the phenomenon is different, so we will not go into that. For the ship, one force acts like this here, one force acts like this here, so it will cause it to tilt like this. So when a ship turns, it will actually be found to tilt like this, heel like this. Tilt means heel. So the ship will go around heeling like this. Okay, this is the phenomenon of turning. Now these things we can easily calculate. That is, so first of all, this is the force, and what is the moment is the distance between the moment will be the force into the distance between the two forces, this force and that force, that is kg minus t by 2. And if it heels, the distance between them becomes kg minus t by 2 cos phi. I am not going to draw the figure. It is exactly the same as the wind heeling. If you remember that, it became hv plus t by 2 last time, hv plus t by 2 cos phi, I derived one. Just like that, L in this case it is kg minus t by 2 cos phi. So the moment becomes kg minus t by 2 cos phi into v square by r t c. This gives you the into delta, this gives you the turning moment. And when you divide by delta, means moment divided by delta, that will give you the turning arm. This is the heeling arm. So this will be with delta, then L turning, or what is, let us call it Tc itself, what they have done will be v square by r Tc into kg minus t by 2 cos phi. Okay.
So can kg minus t by 2 be negative?
Kg minus t by 2 is negative, means let us see, g is, yeah, of course you can always put kg very low, because you can shift all, yeah, it can be negative. So that will mean, in that is a very particular case, it's possible, kg, it's possible, it can be negative. In general it's not, but it can be negative, yes. When you make it negative, then kg is below, the direction is reversed, then the ship will tilt inwards. Yeah, correct. But note that in general kg is greater than t by 2. Kg is for the whole ship, in fact. So and in fact most of the weight of the ship is up in the top region. Yeah, that's where you are putting the cargo and all that. So it comes. So in general, 95% of the cases kg will be. I don't know if there are some cases where kg can become less than t by 2. Some particular type of small boat, probably very small boats, maybe it can happen. But in general, it's like this. So this is that important point. This is another question they generally ask. That is, when a ship takes a circle, will it heel inwards or outwards? You will generally think like a bicycle, it should turn inwards. It doesn't heel inwards, it heels outwards. It's because of this. One moment like this, one moment like this, it causes it to turn like this. And unless this particular case occurs, what you said.
So would the ship be stable during this? Yes, sir.
Will the ship be stable? It is again like this. The stability, again we have to stable means, are you asking will it capsize? For that depends on the moment, heeling moment. It depends on how much it's heeling, and how much it heels depends on what is the turning circle. Kg minus t by 2 cos phi means, as you can see, there is a v square by r Tc. It mostly depends on r Tc. For example, suppose you make r very small. Let me see, how can you make r very small? This is a large r. If I make r smaller, it means like this. It's like this. Means if a ship is like this and suppose it tries to turn like this, that's the meaning of r very small, then it will be unstable. But if it's a large circle, it doesn't matter. That's why you cannot turn a ship like this, it will capsize. Okay.
There will be a small, like the smallest radius for a ship.
There should be a what you are thinking, something like a critical radius where it will, yeah, there should be. For every ship there will be a critical radius below which the ship will capsize. If you try to turn it beyond that, it will topple. That you can imagine itself. Even if it's a simple thing as a car, if you suddenly turn it like this, there is a very good chance that it will topple. Okay. Just like that, it's there for ship also. Yes, it depends upon r. And v also, it depends on v also. If you increase the v, that moment will increase. Means, but a very large speed, small radius if you make, it will topple. But so best thing is smaller velocity, higher radius, it will be stable. Okay. Now there are some relation, this just you have to know, but of course for the end semester, but
Sir, is it possible to turn a ship very fast, sir, like as you do for a car?
no, not like a car, because first of all the medium is water. Water, it doesn't allow you to turn as fast as a air. Air, the resistance is very less, so you can turn very fast. Water, the resistance is much higher, 1000 times in fact. So it cannot turn like that, but if you try to turn very rapidly and in a very small radius, the ship will topple. You can do things like you keep accelerating the ship, you take it to its maximum speed and then you try to turn on a small circle, small radius, then it will topple. That is what we are saying. Then okay, then next thing is we are just touching on dynamic stability from some slightly different point of view. It's not different, but let's look at this. That is, we have already seen that by dynamical stability we mean the work done under the GZ curve. It is the work done by the ship. It is the work done by the ship in opposing the heeling moment. Okay, that is the dynamical stability. So if some heeling moment acts and it's trying to turn it, the ship tries to resist it, it does work there. That is known as the dynamic stability. We have seen that. Now we can derive it simply. First of all, you know that work done is always given by when some force acts between two distances x1 and x2. The work done is usually given by x1 to x2 f dx. This is straightforward. Now suppose that this dx is an arc. Okay, that means this can be written as, so means instead of moving in a straight distance, it's in an arc. So this will be, if I write it as f into r d phi, okay, and it goes between phi 1 and phi 2. All I have done is, it is going in, the arc distance is always given by r d phi. So this is what we are having here. It is a curved distance, okay, that distance it moves. So that is what this shows. From phi 1 to phi 2, if it rotates, it moves a distance of f is some force into r d phi. Now therefore we write f like this, I mean w is given like this. Now this f into r we combine together to write it as m. Okay, therefore this can be written as m d phi. Okay. Now so now what we are saying, suppose we give a heeling moment to the ship. Therefore the work done by the heeling moment can be given as moment due to the heeling or the heeling moment into d phi. This will give you the mh into d phi. This will give you the work done by the heeling moment. Now similarly, the work done by the righting moment will be, this is the work done by the heeling moment, wh is the work done by the heeling moment. Now we have one more thing, we have the work done by the righting moment, wr, it is given by now the righting moment, you know that it is always given by displacement into righting arm. Righting arm is gz, displacement is delta. So delta gz gives you the righting moment. So write that into d phi gives you the righting work done by the righting arm or righting moment. Now suppose that ship is heeling and this righting moment is act. Now the ship will obviously come to rest at a state when the work done by the heeling moment and the work done by the righting moments are same, are equal, identical. Okay. So what happens is, at that stage mh into d phi equals phi 1 to phi 2 delta gz into d phi. Now force oh, actually one thing I missed here. Delta is actually mass, okay. So mass into distance won't give you the moment. Mass into g has to be multiplied, okay. So there should be a g here. So g is to be multiplied here. So it is delta. Delta is, remember, it's the mass of the ship. It's not the weight of the ship as such. It's the mass of the ship. So delta into g will give you, means delta is usually given in tons. As you know, tons is kilogram, 1000 kilograms. So kilogram is mass. So delta into g. So that g should be there. So there is a delta into g here. Therefore, phi 1 to phi 2 mh by g delta. I am just, because delta is a constant, g is a constant, means they are not variables. Delta is the total displacement of the ship that does not change due to healing. Phi 1 to phi 2, here you have gz into, or gz into d phi. Now this I have said, still I will repeat this. It is like saying this, what we have done so far is, suppose this is your gz curve, and here you have your LV. This is your, let us say this is your healing moment curve, healing arm, this is your gz. Now the first one mh d phi represents up to this, let us take let us take this. Now between these two angles of phi 1 to phi 2, some phi 1, some phi 2, in this case we assume phi 1 to be 0, and in this case this, the first one, the first integral represents the area under the, let us call this A1, A2 and A3. So what is the first integral? Means the integral on the left side, integral phi 1 to phi 2 mh d phi represents A1 plus A3, okay, means it is the area under the LV curve or the under the moment curve. Healing moment is this curve, this straight line, this curve represents the healing moment or the healing arm, okay. So area under that curve is A1 plus A3, that is represented by this integral, and the area under the gz curve is the area under this curve, it is A2 plus A3. Therefore what we have done is literally A1 plus A3 is equal to A2 plus A3, or rather that A1 is equal to A2. This is the condition that we are doing. This area is equal to this area. We have done this in the derivation of the wind healing arm also, that is what we did. Okay, now therefore at this angle is usually called as phi dynamic. That is the angle, we remember if we did this in the wind healing arm also, that is when the so what is happening in what this figure shows is, explains is this. Initially the ship is in an upright condition, phi 1 is equal to 0, wind, some healing moment, in this case it can be wind or it can be turning, whatever it is, that healing moment starts acting. Now in that initial stages the healing moment is greater than the righting moment. The moment it starts healing, the righting moment starts acting, because righting moment always comes the moment it starts healing, it tendency to come back, it is like the resistance to that healing moment. So healing moment is greater than the righting moment, and it starts, it keeps going, and it reaches a state when finally the healing moment equals the righting moment, okay, that is this stage. It is a some kind of equilibrium where the healing moment equals the righting moment, but you have to notice one thing, in this process from the upright condition to this moment, the wind or the turning has imparted some energy from into the ship. That is because there is a difference in area between the, so this area, first of all some work is done by the healing moment on the ship, that is the area under the healing arm curve, then work is done in resisting it. That excess work done by the healing on the ship is given to the ship, it is like an energy given to the ship. So even though it has come to this dynamic equilibrium, in this static equilibrium case, it has an excess amount of energy. This ship now has an excess amount of energy. That energy causes it to heal further. Okay. Even though, that is why even though the forces are balanced, the energy is still more for the ship. Ship has some excess energy, therefore that ship continues to heal further, and the moment it crosses this static equilibrium case, the resistance is more than the, still that wind moment is acting, but the resistance is now more than the wind healing moment, but energy is there causing it to heal further, and till that energy dissipates, till that excess energy dissipates, it will continue to heal. Therefore, though this is some kind of equilibrium, it will continue to heal it till it reaches phi dynamic. So we can say that phi dynamic is like a possible state when it will definitely stop. Okay, after that ship will not heal further definitely, and therefore this is the condition, this is the concept of dynamic stability. Okay. Okay. Now here actually they have done something which I described below, because someone asked me at that time, which is a, what is the really a worst condition. It's, they are talking about this condition here, that is they are showing here, though it is not really explained probably, it is like this, that is the concept is this, that is you have a pendulum hanging like this. So there are three possibilities: pendulum hanging like this, a push is given to it, that means that healing moment is given to it, or I am giving some energy to it, it moves like this. Then it is in a condition like this, it has some, then I am giving a push to it, that is one possibility. Then it is like this and I am giving a push like this, that is a third possibility. In which of these conditions will it go to a maximum? Okay, that is a question. Though it, you might think that like this, it is already in some healed condition, won't it go to the further? It is not correct. That is not where it will heal further. If it is like this, what will happen is that if it is like this, when some energy is given, it already has a potential energy, because it's not in this case. Okay, let us take this case, pendulum is exactly vertical, it is upright, ship is in the upright condition. In this case, it has literally zero potential energy. So whatever energy you are giving causes it to move like this. Then what they are saying is that if it is like this, that potential energy added will cause it to move further. Okay, that additional potential energy adds to the energy already available to move further, whereas in this case the addition, it has less potential energy, which cause that it has like negative potential energy, which removes from the energy added. So what the, though it is not exactly explained, the thing is this: a ship, let us say, you can think, that is when you have pendulum in these three conditions, when you take it like this and you give it to a push, it will go further than if it is like this, you give the same push, if then like this, if you give the same push. That is the law. Okay, that is what will happen. Okay, that you actually think of it in energy terms, you will figure it out. Okay, it is the same thing for a ship. If it is ship is like this and you give a push, it will, that inertia or that force due to its motion itself will cause it to move further than it would if it is in the condition, in the upright condition. Like it is like this, some kind of additional force comes to it, some energy is given by the wind itself, but when it is turning, an additional force comes to it which causes it to move further. Okay, so that is a condition in, though it is not given any, explained any further than this, but okay, that I do not think it is anything more is explained than this. It says that the energy transferred from the push, which is the energy given by the moment, is added to the potential energy accumulated by the swing. That means while coming from here, some potential energy is accumulated by the swing while it comes like this, because of that will add to the energy and it will cause it to go. When it is like this, it is like instead of potential energy accumulated, it is like potential energy lost from the swing, that much energy will be lost from the energy given by the push itself. Okay, so this actually goes completely against your intuition, but that is the what happens in by physics. Okay, then all right, then we go into a little bit about equations of motion. So it's like this, that is, first of all, we write, the equation of motion is, first is ma is equal to, or m into d square, no, m into dv by dt, I will write it in this way, m into d square x by dt square is equal to net force. This is the first Newton's law of motion. Okay. Now, similarly, if you consider the rotational case, it will become I into I omega square, that is half I omega square is known as the rotational energy. So it's like this, the equation becomes I into d square phi by dt square will become the moment. Okay. This is the Newton's equation in the rotational case. So I into d square phi by dt square, d phi by dt is omega. Okay. So d square phi by dt square is your omega dot. So I omega dot is equal to the moment or the external torque acting. Instead of the force you have the torque, and instead of mass you have I, and instead of d square x by dt square is you have the phi. So this is your rotational condition. So that same equation we apply here. Now the right hand side indicates the net moment, which is the healing moment minus the resisting moment. The resisting moment is the righting moment, which is g delta into gz. Okay, that is the resisting moment, and the other one is the healing moment. So healing moment minus that will give you the net. This is a case when the first part of the problem means when the healing moment, in this case we represented this region where the healing moment is greater than the righting moment. This is bigger than this, that is what this figure. From here this becomes bigger than this, that is a different part, that we are not bothered right now. We are talking about this case where the healing moment is greater. So the net moment is this minus this, that will give you the net moment. So the healing moment minus the righting moment will give you, j is still the same thing, our I, but slight difference is that till now we talked about area moment of inertia in our earlier things. This is the mass moment of inertia, like ma is the act force, like that I related with m is the mass moment of inertia, mass moment of inertia. Therefore this becomes, j is actually defined as okay, square is there what, m, yes, m y square. So this is known as the mass moment of inertia. So this is j. Now once you have that, so this equation, this we rewrite it as j d square phi by dt square plus g delta gz is equal to mh. Okay, this is the equation. Now we will do one thing, we will add a d phi to all the terms, d phi, d phi, d phi. Then now this j factor, that is, let us take this component that comes with j, d square phi by dt square d phi, this term, this we write it as, now d square phi by dt square can be written as d phi dot by dt, where phi dot is d phi by dt. Okay. So d phi by dt, d by dt of that is known as d square phi by dt square. So d phi dot by dt into d phi, which is equal to, which I still write it as d phi dot by d phi into d phi by dt into d phi. Now I remove these two d phi's, this becomes d phi dot into phi dot. If you have some doubt with this, you can ask me. Any of these, one going to the other, if there is any doubt in that. You have d square phi by dt square d phi. Now, this is d by dt of d phi by dt. Now, d phi by dt I write it as phi dot, which is against d phi by dt only. So, d phi dot by dt into d phi. Now, here I just divide by d phi and multiply by d phi. So, this becomes d phi dot by d phi into d phi by dt into d phi. Now, d phi is cancelled. Therefore, d phi dot into d phi by dt is phi dot. That is the definition of phi dot. We are defining it like that. So, d phi dot into d phi dot, okay, phi dot into d phi dot. This is your this we are slightly rewriting it as this. So, j into the equation becomes j into phi dot d phi dot plus g delta into gz d phi is equal to mh d phi. Now, we will integrate this expression between two values of phi 1 and phi 2, or phi 0 and phi final. Phi 0 means the phi 1, phi final is the so j into integral of phi 0 to phi f phi dot d phi dot plus g delta gz g delta into integral phi dot to phi f gz d phi equals integral of mh d phi between phi 0 and phi f. Okay. Okay, now I will just take this, keep this here. Now, this I will become, this itself, what does it become? J into half phi dot squared final minus half phi 0 dot square plus, or that is equal to mh d phi phi 0 to phi f minus g delta phi 0 to phi f gz d phi. Okay. Is there any problem with any of the steps? You see how we have got this now? Means integral of something, integral of x dx is x square by 2. Integral of x dx is x square by 2. So, in this case x is phi dot. So, phi dot squared by 2. So, phi dot squared final minus phi dot squared initial by 2.
So, but phi dot initial is not phi naught, phi 0.
No, no, phi dot is not initial, but it is phi dot. Oh, it's, I shouldn't have written like this. That's correct. That's a good point. Okay, left side I'll write again j into j by 2 into phi dot squared at phi f. Maybe I'll write like this. Okay, minus phi dot squared at phi 0. Okay, yeah, this is the correct way I should write. So, this is equal to this right hand side. Okay. Okay. So, this now what is this left hand side? Half, it is actually j, remember, is I, a moment of inertia. So, half j, what is phi dot? Phi dot is omega. Okay. So, half j omega square is actually the rotational kinetic energy of the system. So, you have two components here, there is a rotational kinetic energy and there is a potential energy. Okay. So, left side represents your kinetic energy, of course, it is rotational, it is the kinetic energy of the system, this thing. Now, now in the case of, so there is a total energy of the system which will be a sum total of its kinetic energy, rotational kinetic energy, there is no translational kinetic energy here. Of course, ship is moving, that is a different thing, we are not bothered about that. So, let us just consider the sum total of this rotational kinetic energy, and there is, because of its tilting, there is a change in its potential energy, because g will, because of movement there will be a change in, let us see why exactly should the potential energy shift. Potential energy changes, Yeah, G is shifting vertically because it is healing some mass, because it's healing some masses are coming down, it vertically it's moving, there is a movement vertically of the whole mass, therefore G is shifting, therefore there is a change in potential energy because the G is moving. No, total mass is the same, but the G is moving, as a result of which there is a change in potential energy. So the potential energy plus rotational kinetic energy represents the total energy of the system. Now in a stable condition your potential energy will be minimum, that is a basic law. Okay, your potential energy is minimum means you have a stable condition. For example, you have a pendulum, the pendulum is stable when z equal to 0 at the lowest most point. At this point pendulum is not stable, potential energy is not smallest, it is high, there it is not stable, potential energy is high. So potential energy is low means the system is stable, therefore when you should have the minimum potential energy, which means that you should have the maximum kinetic energy. I am talking about the stable condition in case of healing. So your rotational kinetic energy should be maximum, that seems to be the condition for stability, that will be when your potential energy is minimum. Okay, so your kinetic energy should be maximum, your kinetic energy should be maximum, that means the left, if k is the kinetic energy, then that means dk by d phi should be equal to 0 when kinetic energy is maximum. I am saying dk by d phi should be 0 and d square k by d square phi d phi square should be less than 0. This is the condition for maximum kinetic energy. That means at what phi is k maximum, that is what we are trying to find, at what phi is k maximum. Therefore dk by d phi should be 0 and d square k by d phi square should be less than 0. That means the left, so this represents k. As we have seen, this equation states as this value is equal to this value. So d by d phi of this is equal to d by d phi of this right side, which means mh minus g delta gz should be equal to 0. This is one condition, the first condition. This becomes like this, which means that mh should be equal to g delta gz. What does it mean? It just simply means that your healing moment and your writing moment should be the same. That is a condition of stability, that is straight away we know, but that is not enough. This is also to be satisfied. Okay, then only you will have the minimum potential energy or maximum kinetic energy. Now that condition means the right hand, so d by, you have to do d by d phi again, therefore this becomes d of mh by g delta by d phi will become less than d of gz by d phi. Okay. Now this is also very obvious. What does this indicate? I will tell you what it indicates. That is, suppose you have this now, what it really, first condition says, what it says is that the healing moment and the writing moment equals, like this point. This is a condition of equilibrium, stability, lower potential energy, so it is a condition of stable. Then our next condition, what does this mean? It means that the slope, this is the phi and this is the moment, so the slope of this should be less than the slope of this. The meaning of that is, if the slope of this is smaller and if this than the slope of this, the meaning of that is it goes up, this goes up and this is coming down, means the moment you cross this point, this curve will be above this curve, that is the meaning of it. That means from that point up your writing moment will be greater than your healing moment. When you do that, resistance is more, there is a tendency to come back, there is no tendency to go further. Okay, so it is a position of stable equilibrium. Stable equilibrium means it might go, but the healing moment might cause it to move. If it tends to move, then the writing moment becomes more than the healing moment and it comes back to the original position, so it stays there. That is the meaning of this mathematical inequality. okay, this less than equal to, less than expression, the meaning of that is d by d phi of this thing is less than this, meaning is that the slope of this curve should be less than the slope of this curve. The meaning of that again is, if the slope of this curve is less than the slope of this curve, when you cross this phi, this value of phi, let us call it phi dash, the moment you cross that, you will have a higher gz than an LV, or the writing moment will be greater than the healing moment. This value will be higher than this value. If this slope is in this fashion, if this is going down and this is going up, this value will be higher than this value the moment you cross phi dash. Therefore, your healing moment will become less than your writing moment. Writing moment, remember, is always the resistance to motion. If the resistance is greater than the healing, then there is no motion. That is all we are saying. So, it is a equilibrium, stable position. So, what happens if it is the other way around, like it is like this, let us say. Let us take this case, this position, okay. What happens here? Here is the other way around. The moment it crosses here, Gz is below the, this part alone we will draw. This is Gz. Gz is below the healing moment curve. So, writing moment is less than the healing moment the moment it crosses this. So, what does it mean? Healing moment is always greater, or the writing moment is always less, the resistance is always less than the force acting. That means there is always motion, it will continue to move. Therefore, whatever it is, the moment it crosses this phi 2, it will continue to move only, because the resistance is less than the force acting. So, the force causes it to keep moving and it will capsize. There is nothing to stop it from capsizing, it will continue to happen. But it is different here. At this point, if it moves further, the resistance is more, as a result of which it comes back to its original position. The only reason is the relative position of the Gz and the healing moment curves. So, this is the Gz curve and this is the healing moment curve. The relative position is what determines whether it is going to capsize or not. Okay. So, from this one curve we can say these two things, whether it will capsize or not, just looking at the relative position of the Gz and the healing arm. So, there are two positions of equilibrium here, you can see. In both cases you have the writing arm is equal to the healing arm, but at this point it is stable, whereas at this point it is unstable. Okay. All right. Then now there is something known as roll period. Okay, that is, let us write that equation. Let us consider first there is no healing moment, means nothing is there to cause the ship to heal as such. There is no wind, there is no turning, nothing, it is just moving in a straight line. But at that time also healing can happen, okay, it will keep moving, that is called rolling. In fact, means the ship even though there is no such external force, due to some reasons it will always, because of its motion itself, it will cause it to move a little bit like this, okay, that kind of rolling will happen. Now, the equation, previous Newton's equation becomes like this. It was a G delta Gz is equal to 0, okay. That means I have just set the healing moment to 0. So, mh is set to 0, therefore, j into d square phi by dt square plus g delta Gz is equal to 0. Now, remember the formula, Gz is equal to gm sin phi, okay. There is such a formula which you have to remember. So, j into d square phi by dt square plus g delta gm sin phi equal to 0. Now, let us consider small angles of heel, that is phi in the range of 0 to 15 degrees probably. therefore sin phi is equal to phi, therefore j into d square phi by dt square is equal to g delta gm phi minus. Okay. So what is this? This is the equation of simple harmonic motion, okay, where you have your acceleration proportional to displacement or minus displacement, that is known as the simple harmonic motion. So in this particular case, it's just happening, it's just because of this condition the ship is just going in a simple harmonic motion like this. Even though there is no heeling moment, it is still going in a simple harmonic motion because of its motion, it's causing it to heel like this. And from this you can directly get the expression for the time period of that simple harmonic motion. It will become now there is one simplification we can do. This moment of inertia can be written like this, okay, that is, or in general words you write it like this, that is where k is known as the radius of gyration or gyration or something. Okay, so k is the radius of gyration, what do you call it? Gyration, no? Radius of gyration. Okay. So so this j, if you write like this, delta is the mass of the ship in tons probably. So Im is the radius of gyration squared, Im is the radius of gyration and that squared. So this is j. So we write it like this, Im squared into delta into d square phi by dt square equals minus g delta gm phi. So delta gets cancelled out. So from this we can get an expression for the frequency of the rolling. So that is given by omega 0 is equal to root of g gm by Im squared. Okay, this is omega 0 is equal to root g gm by Im squared. This is the expression for the frequency of rolling, or from this you can get the time period. 2 pi by omega will give you the time period. So this gives you the frequency of the rolling motion. Okay. Now this tells you this, in fact we have derived this expression in a slightly different form sometime before. What this shows is that again that gm is dependent, this frequency of rolling, I mean that derivation was done from a slightly different direction, but still the expression was the same. So what you are seeing is that the frequency of rolling is dependent upon gm, or the rather the time frequency is directly proportional to root gm. So time period will be directly proportional to 1 by root gm, right. So if you keep increasing the gm, same concept, if you keep increasing the gm, we know that it's good from our stability point of view. If you increase gm, when gm becomes greater than 0, it's stable. Like that you keep increasing gm, the stability will keep increasing, but when you keep increasing gm, the time period will keep decreasing. So it will become like this. Okay, when it is time period is less, it will become like this, lesser and lesser, it becomes like very fast like this. If the time period is higher, it will become slowly like this, it will start moving. This is very comfortable actually. When it is very slow, we won't even feel the movement, otherwise it will be moving like this. So that is a reason for not increasing gm too much, because the ship will become highly what is known as stiff. The word is stiff, means the ship is like this, this is called stiff. The other opposite of it is called tender, it's very good, okay, it's good for us. But of course that means you keep decreasing the gm, that is also not very good, because from the stability point of view that might affect you. You keep decreasing gm to a very low value, so somewhere you have to do an optimization, somewhere that is some intermediate value you choose where you have a value of gm such that both are okay, it's not too stiff, it's not too unstable. Okay, this is the now well, this is not that important, but still there is something known as, I mean this was proposed by Kempf, and there is a something known as a Kempf factor, which is defined as now in general it is known that we haven't done it, so you won't know. So there is a relation between GM, not a relation actually, but it's like maximum limit between GM and the breadth of a ship. Okay, there is some relation, there is some form of relation between the, for a stable condition, what will be the relation between the GM and breadth of a ship. So he brought in a there is, wait a minute, what is it, T into root G by B. This is actually this is not important. It's just know that there is something known as chem factor. This is the exact expression for it. It's like T is the draft, T into root of G by breadth. Now when the chem factor is under 8, you say that this is, and if it is less than 8, then you say that the ship is stiff. If it is 8 and 14, we say that it's comfortable. Okay. I guess you can just know that there is a chem factor, because these things are not probably not that important, but know that this chem factor is defined such that if it is less than 8, you have a stiff ship. This factor so this is chem factor is used in designing a ship. When you are designing the GM, you do not always go to a maximum. There is definitely very strict requirements that say that GM should be a minimum so much. So you come to that minimum, you design the ship with that minimum, then everybody tries to increase the GM, because then it will become more stable. So while going in the other direction, you keep increasing the GM, you check this and make sure that chem factor is in 8 to 14 range. So once it's outside this range, it becomes stiff. At least it should be 8. You try to put the chem factor 8 such that your stability is maximum, and then it's okay, then the ship is okay. All right, so I'll stop here. Thank you.